Hello, and welcome to the OMNISEC demo at your desk. I'm Kyle Williams, an application scientist at Malvern. Today, we'll take a look at the OMNISEC GPC system. We'll look at the individual components of the instrument, run some samples, and then work up the data. This demo is intended to provide you with a glimpse of what it's like to use the OMNISEC system and software. You ready? Let's get started. So OMNISEC is comprised of two components: Resolve, which contains the pump, auto sampler, and column compartments, and Reveal, which contains the detector compartments. This way, the system is divided into a chromatography unit and a detector unit. So now let's take a closer look into each of the compartments. Let's start with OMNISEC Resolve. So OMNISEC is a GPC system, and like all liquid chromatography systems, it requires a mobile phase to carry the sample through the instrument. That mobile phase, THF in this case, is situated on top of OMNISEC Resolve. Color-coded tubing identifies which lines go where in order to minimize mix-ups. The mobile phase line is green, the autosampler wash line is clear, and the waste is yellow. If we follow the flow path of the instrument, the first compartment that we come to is the pump compartment. Before the mobile phase even gets to the actual pump, it is pulled through the low-volume vacuum degasser. This removes any dissolved gas in the mobile phase in order to keep detector baselines as stable as possible. The low-volume aspect of it means that switching solvents is easy, as there is little solvent to exchange in the degasser. Next up is the low-pulsation pump, which moves the mobile phase through the system. The mobile phase path through the pump provides back seal washing, which helps keep the pump components clean and prolongs their lifetime. From there, the mobile phase moves through a purge valve, which allows you to quickly prime the pump when it is open, and then through an inline filter, typically with a membrane of 0.2 micron pore size, before moving to the next part of the system. Next in the flow path after the pump comes the auto sampler, which is situated at the bottom of OMNISEC Resolve. The auto sampler has temperature control of the sample compartment, ranging from 4 to 60 degrees Celsius, to help keep the samples stable in solution while they await analysis in one of the two 48-vial trays. During injection, the sample is transferred from the auto sampler vial to the sample loop with a syringe that provides accurate injection volumes down to at least 5 microliters with no overhead. Once injection occurs, the mobile phase, now with the sample, moves to the column compartment, where the separation happens. The column compartment is temperature controlled from 20 to 65 degrees Celsius to accommodate a range of applications, and large enough to house the column set of your choice. The separate compartment for the column set and post-column filter make it easy to get to the most frequently accessed system components. After the sample has been injected and has been separated in the column set, it travels over to OMNISEC Reveal to pass through the array of detectors. OMNISEC Reveal contains two compartments. The top compartment houses the UV-Vis photodiode array detector, shown here. This is actually just to provide access to the bulbs of the photodiode array detector. The actual sample cell resides in the bottom compartment. The four detectors, refractive index, UV-Vis PDA, light scattering, and viscometer, are situated in a single compartment. This minimizes inter-detector distances and band broadening, as well as provides excellent thermal stability. The temperature of the detector compartment can be controlled, just like the column oven, from 20 to 65 degrees Celsius to cover a wide range of applications. Additionally, just as the PDA bulbs are easily accessible from the top compartment of OMNISEC Reveal, the viscometer bridge and the delay columns are easily accessible for quick maintenance. After the sample elutes from the detectors, the waste flows back through the pump compartment through the yellow tubing to a waste bottle located on top of OMNISEC Resolve. So now that we've gone through all the system components of OMNISEC, let's set up a sample sequence and analyze some samples.
So the first thing we need to do in order to run some samples is to go to the sequence page. So we're on the home page now. So to get to the sequence page, we can click on the tab at the top of the screen. Now we're presented with a blank sample sequence. So the first thing we can do is name it. We'll go ahead and title this one something Demo Sequence 1. And now we can begin to enter in the information for our standard and samples that we're going to analyze in this sequence. So the first sample name will be our narrow standard, polystyrene 105,000 Daltons. The next thing we can do is set the sample type. So we can come through here in the database and select polystyrene and THF, since our standard is a known sample type. Enter in the rest of the relevant information, such as concentration, the injection volume. Total number of injections is 2, so we're going to do duplicate injections of each sample, and the vial number as well. So it's in A1 on the left tray, so the first vial. And we move to the next sample, polystyrene 235,000 Daltons. The sample type is the same. Enter the concentration. The second sample, or the third line, is going to be a polymethyl methacrylate sample, so we'll have to come back into the sample type database and change it back to polymethyl methacrylate in THF. Enter in the new sample concentration. Again, we'll do a full 100 microliters injection, 2 injections, duplicate injections. The vial number follows 1, 2, 3. So then we can look at our run conditions and run parameters, which are on the left side of the screen. We can go to the database and set up THF as our mobile phase. Next, we can move and choose the correct column set, which in this case is mixed bed columns in THF. And the last thing we can do is check our run length, which is going to be set for 45 minutes. So now that we've got our sequence and our run conditions set up, the next thing we should do before hitting inject is do a baseline monitor. So I always like this to be the last thing I do before I hit start, is to monitor my, the current level of my detector signals to make sure all baselines are stable. Right now we're looking at the signals, they're on auto scale, so what may look like noise, if you look at the appropriate scale for the detector, may actually be very minimal noise. So everything looks to be pretty good. So let's go ahead and stop the data acquisition. No need to save it. Our detectors look good. So if we go back to the sequence tab, just do one last check, make sure everything's correct. Since we're about to inject, let's take a look at our needle, and then we hit start. And we can see, as indicated by the green arrow on the left, the instrument status bar on the bottom left of the software screen shows you the instrument status, what's currently happening. So right now we're doing an initial wash of the needle and the entire injection path, in fact. And so this full wash takes place at the beginning of every sample sequence. Not every injection, but every sample sequence. After each injection, as we'll see, the instrument will do a separate individual wash after each injection. So right now it's rinsing out the entire path that the sample will come in contact with, the needle, the tubing, and the sample loop, flushing that with solvent before the needle moves to the sample vial. And now it's drawing up sample into the sample loop. And now after the sample loop is full, you'll hear a noise, and that will turn the valve, which will essentially inject the sample right there into the flow path. And so now our sample has been injected, and we're doing that one last wash of the needle after injection to make sure that there's no cross-contamination between samples. And you can see data is already being collected on the screen. And now our sample wash is complete. And so instead of sitting here and watching 45 minutes of slow data acquisition for each sample, we're going to go ahead and take this time to look at some background theory on GPC before we come back to these chromatograms. So to start back at the beginning, GPC stands for Gel Permeation Chromatography, which is a type of Size Exclusion Chromatography. GPC describes an analytical technique that is used to characterize macromolecules, providing data such as molecular weight, intrinsic viscosity, and hydrodynamic radius for a variety of sample types. Examples of materials frequently analyzed by GPC include natural polymers, synthetic polymers, and proteins. As a type of size exclusion chromatography, GPC separates molecules based on size. But how does it work? Well, if we take a close look at the inside of a GPC column, we can see that the column gel is made of particles that contain pores. The presence of these pores is the key to making GPC work. The separation process operates based on the diffusion or permeation of the analyte molecules in and out of the pores on the column gel. As we can see in the animation, the largest molecules, represented by the triangle, spend the least amount of time inside of the porous gel particles. The intermediate sized squares can diffuse partially into the pores before moving to the next, while the smallest circles can easily diffuse in and out of the pores, penetrate all the way in, and thus require the most time to elute. For more background information on GPC, please see our YouTube video titled Introduction to GPC in 30 minutes. Shown here is a schematic for a complete GPC system such as OMNISEC. The columns and chromatography process we just described are located in the center of the image. OMNISEC Resolve contains the columns as well as the other system components shown, such as a mobile phase reservoir, a vacuum degasser, the pump, and the autosampler. OMNISEC Reveal contains the detectors, which provide information on the sample after it has passed through the column set. The most common detectors used in GPC are a refractive index detector, a UV-Vis photodiode array, a light scattering detector, and a viscometer detector. The refractive index detector responds to sample concentration. The UV-Vis photodiode array responds to sample concentration and light absorption. The light scattering detector responds to the sample's molecular weight, and the viscometer detector responds to the intrinsic viscosity of the sample in solution, which is influenced by the sample's molecular density. Advanced detection, also known as triple or tetra detection, combines the data obtained from all of these detectors to provide a wealth of molecular characterization data. It is important to remember that since advanced detection uses a light scattering detector, the molecular weight values obtained are absolute molecular weight values, meaning no calibration curve is necessary, as the molecular weight is calculated independently from the light scattering detector. Additionally, with advanced detection, a single narrow standard is used to determine the instrument constants and detector offsets. The accuracy of data is independent of the standard, and that each detector tells a different piece of the story. Sample concentration from the RI and the UV-Vis or photodiode array detectors, sample viscosity and size information from the viscometer detector, and molecular weight from the light scattering detector. And last, with advanced detection, there is an incredible amount of data available from a single injection. Molecular weight moments, intrinsic viscosity, hydrodynamic radius, radius of gyration, structural information, concentration, recovery, and potentially absorption profile and compositional analysis. So now let's take a look at how we can use OMNISEC to obtain all of this data for the samples we left running. So let's pick back up with our analysis, but in the interest of time, let's look at the sample acquisition at 180 times the normal speed. This will allow us to watch 4.5 hours of sample acquisition in about a minute and a half. You can see all of the detector signals acquiring data simultaneously, and just like with the baseline monitor, the autoscale adjusts the axes in order to provide the optimal view. Here you can see the solvent peaks from the RI and UV detector, and now the negative peak from the delay columns of the viscometer. As we move on to the polystyrene 235,000 sample, we see the broader peak shape, which is to be expected from a broad sample as opposed to the previously acquired narrow standards. So as the first injection of the PS235 wraps up, then we'll move along to the second injection. At a glance here, we can see that the peak shapes of the two polystyrene 235,000 Daltons look very similar, indicating they're consistent. Now as we move along to the PMMA 93,000 Dalton samples, the first thing we notice is that as the peak elutes, there is no UV signal, or there's no peak in the UV signal, which is actually expected since PMMA does not have a chromophore like polystyrene does, and so there's no absorption, nothing to provide a UV signal for PMMA. So it looks like we're almost done, and once we're done, then we'll move on to data analysis. All right, so now that our samples have finished running, let's take a look at the data and see what we got. So first, let's go up to the Analysis tab to open up the Analysis workspace. Second, let's go to Open Data, so we can come over here and select Demo Sequence 1 to open all 6 injections we ran. Get Selection. Now we'll open all 6 injections in the record view, and we can use this to move back and forth between injections. So the workspace is split up into multiple windows. Here on the left, we have our numerical data, our polymer results report. Top right, we have raw data, which essentially shows the entire chromatograms that we acquired. And then down below, right now, we have derived data, which shows results. Since we haven't created a method and calculated any results, there is nothing to show in that window. But as soon as we set up a method and calculate results, we'll see what the derived data window can offer. So since we have our narrow standard open, let's go ahead and set up a calculation method using this narrow standard. So in order to do that, we come over here to the Create a New Calculation Method button. Click that, and the method window pops up. Let's go ahead and name this method. After we name it, we choose which detectors to use. In this case, refractive index, light scattering, and viscometer, which will give us a full triple detection method. Once we've calibrated it, the method, the band broadening, and detector offset values will appear on this screen, but since we haven't done that yet, there are no values to show. The analysis type, we're going to calculate concentration from the sample DNDC. This is because when we were setting up our sequence, remember, we assigned the sample type to our sample, which assigned the DNDC for that sample type to the sample. And so we will use that DNDC in order to calculate the concentration of our sample. Now, we know that the DNDC for a sample is not always known, and in that case, you have a few other options. The first, to calculate the DNDC from the sample concentration, which means that it takes the input concentration that we entered in the sample sequence, and the software will calculate the DNDC for the sample based on an assumed 100% recovery of that concentration. The second, which is what we're using, will calculate the concentration from the sample DNDC. And the third, if you're doing a bunch of routine analysis of the same sample type, then you can set the DNDC in the method, and that means any sample you analyze with that method will use that DNDC value. So we're going to use the second one to calculate concentration from the sample DNDC. The calibration standard we can choose here, but since we haven't set limits or baselines, we're going to go ahead and select that after we've set those. And the Mohs parameters, if you're using a multi-angle light scattering detector, the Mohs parameters would appear here. So we're done, so we can save the method. And now we can go ahead and set limits and baselines around our narrow standard. And let's go ahead and use the auto limits and baselines. And in order to do that, we just click the Find Limits button, and the software will automatically place limits and baselines around the peak. And so now that we have limits and baselines around our standard is defined. Now let's come up and select Calibrate to calibrate our method. And when we do that, it opens up the calibration database in order for us to select the appropriate standard. In this instance, we're using a polystyrene 105,000 Daltons in THF. So we can choose this, select it, and as soon as we do, then the method calibrates and you can see the molecular data updates, and now we have data in our derived data window. So now we have a calibrated method that we're ready to use to analyze other samples. So this has calibrated the detector offsets, response factors, and band broadening corrections all in a single step, which makes it as quick and simple as possible to calibrate the system as needed. So now that we've set up our method, let's use that method and analyze another sample. So if we come over to our record view and select the polystyrene 235,000, first it's going to ask us if we want to save the results that we just analyzed and created for the PS105. We say yes. And so now we've opened the polystyrene 235,000 Daltons, and since we haven't analyzed it yet, the derived data in the polymer results table are blank. So let's go ahead and set limits and baselines around the peak. As soon as we do, those results will appear. In this case, since we did auto limits and baselines last time, we'll manually set our limits and baselines here. And to do so, we hold Shift and then left click on either side of the peak to set limits. And if we hold Shift and right click on either side of the peak, we'll set our baselines. And once those have been set, as expected, the molecular data appears and we get the results in the polymer results window and the derived data window. And you can see that the molecular weight is about 235,000 Daltons. In addition to other molecular weight moments, the IV value, hydrodynamic radius, RG, Markooing parameters, and then recovery, or another way to look at concentration, are available. So in this case, we can feel confident that we set up a valid calibration method because we're able to confirm it with another known standard of known molecular weight. So now that we've set this up and we're confident in our method, we can move on to unknown samples. Our unknown sample in this case will be the polymethyl methacrylate 93K, so a sample of a different type. So let's go ahead and analyze that by first coming to the record view and selecting it. And again, we will save our previous results by clicking yes. So here's the data for our PMMA 93K. Let's go ahead and let the software find our auto limits and baselines. And once it sets the limits and baselines, they're not set in stone. You can click and drag to adjust them as you see fit, and the derived data view or numerical data will update in real time accordingly. So we've got data for the PMMA sample, as we see, 93,000 Daltons, comes out as expected. Let's go ahead and analyze the other injection as well, just to make sure we were consistent between injections. So to do so, let's just move down to the next sample, or the next injection of the sample. Auto limits and baselines. Go ahead and just adjust the limits a little bit. See the molecular weights pretty close. We can go ahead and, instead of waiting for the software to prompt us to save, we can come up to the toolbar and click Save to save the results as well. So now let's look a little bit closer at the derived data window now that we've got some interesting results. I'm going to go ahead and maximize this window by clicking the expand icon in the top right of the window. And so what we're looking at here are the detector signals between the limits of integration. And so if you wish to see more of the chromatogram, you can toggle back and forth between showing the entire chromatogram or showing the peaks, or you can adjust the x-axis by using the scroll wheel to get the view that you want. And in addition to the data, we're now able to add other results on top of the figures. And so you can see on the right, there's the axis for the log of molecular weight. And so what this is this is the calculated molecular weight over the entire molecular weight distribution. And again, you can adjust this axis as well with the scroll wheel to get the view you want. Now we can add other types of results onto the derived data window by coming up to the toolbar. Let's say we want to add the intrinsic viscosity and hydrodynamic radius. We can add those as well, and again adjust the axes and move them around to get the figure that we want. Another thing that's really nice about the derived data window and all figures in OMNISEC is that they're easily transferred graphically and with the data to commonly used Microsoft Office applications. So if we want to add this figure and paste it into a PowerPoint, we can simply right-click, copy the graph, open up PowerPoint, and paste it in. And then we can adjust the figure as we see fit for our presentation or report or whatever we're doing. Additionally, if we right-click and select Copy Data, and we can open up Excel and paste in the numerical data if we want to create our own figures, and you can see we get all of the data available from that particular plot. So since we're looking at the derived data plot that has calculated results, and so we're getting all of the calculated results that are available in the derived data plot. So now that we've looked at the results in calculated data for a single sample injection, let's go ahead and look at the data for 2 sample injections of the same sample and compare them. In order to do that, let's use the overlay data, which can be accessed by selecting the option from the drop-down title at the top left of the window. So if we select overlay data, now what we're looking at is a single detector channel, in this case the refractive index, for all of the samples that are selected. Since we only have one sample selected now, let's go ahead and select both of the injections of the PMMA 93K. To do so, I'll hold Control and click both samples. And so you can see the color-coded dots over on the left correspond to the color of the chromatograms shown for each injection. So right off the bat, we can tell that they look very similar. We would expect our results to be similar. We can switch back and forth between detectors. We can look at the right angle light scattering detector, the low angle light scattering detector, the viscometer, and make comparisons between different injections of the single detector. And in addition to the detector response, since we've analyzed this data and have saved results for it, we can also overlay a single result type on the window. So if we select molecular weight, now we're looking at the overlay of both molecular weight plots for injection 1 and injection 2. If we want to look at intrinsic viscosity, we simply click that and it'll update accordingly. So with the overlay view, you can look at a single detector channel and a single result type for multiple samples selected from the record view. In addition to making these visual comparisons, if we minimize the window, when you highlight multiple samples in the record view, you now open them up in the results table as well. And so we can see now that we have 2 columns of results representing the data for injection 1 and injection 2. And as expected, for 2 injections of the same sample, the numbers are incredibly similar all the way up and down the line. And we can confirm that by looking at this result statistics table at the bottom, which shows the average retention volume, molecular weight, and recovery, and also includes the percent relative standard deviation of both injections, all well below 1, indicating extreme precision between injections. So now let's use this overlay view to look at comparisons between 2 different samples instead of 2 injections of the same sample type. So let's come up here and let's select the polystyrene 235,000, and we'll hold Control and click the 93K PMMA. And so now, as expected, the numerical data in the results table are very different. We can see the 235,000 Daltons for the polystyrene, 93,000 Daltons for the PMMA. Of course, our result statistics table don't make nearly as much sense when we're looking at 2 different samples, but we still have the data available. Of course, these results tables can be customized and configured to best fit your needs. For example, I have a separate report that distills this wealth of information down to the essential molecular weight, IV, RH, and recovery values. and that's, I can quickly toggle back and forth by coming up here to the drop-down menu and selecting the report, which I've titled Relevant Data. When I click that, you can see that it's simply the molecular characterization values that I've highlighted and choose to see. But where this is really interesting is in the overlay data chromatograms. So I'm going to maximize this window again, and we can really see here the difference between the chromatograms and the sample peaks. In this case, the retention volume is different, and so you see the polystyrene elute earlier as it's much larger than the PMMA. And if we look at the log molecular weight curve, let's go ahead and bring that a little more on scale. You can see that the log molecular weight for the polystyrene extends to a much larger range than that for the PMMA. So this is a really nice feature for creating visual comparisons between two different sample types. And the last thing I want to point out when comparing two samples is that we can use the distribution plot to access the Markowing plots for the two samples. So if we select distribution plot from the drop-down menu of the window title, then, and let's go ahead and maximize this window. For all samples that are selected in the record view, we can see the Markowing plot, which plots the log of IV versus log of molecular weight and allows structural comparisons to be quickly and easily made between samples. Because we're essentially looking at molecular density on the y-axis with molecules that are more dense existing lower on the Markowing plot, we can tell here that the PMMA sample is more dense than the polystyrene sample. So this is just a single example of the structural differences that appear between two different sample types, but conceptually this is the same as to how we investigate and look at branching in a sample, where when you have a highly branched material, that material becomes more and more dense with increasing molecular weight, and so that difference in density creates a downward curve in the Markowing plot.
So today we've taken a look at OMNISEC, including the hardware and the software that comprise this complete integrated GPC system. The pump, the auto sampler, and the column oven are housed in OMNISEC Resolve, the chromatography unit. And the detectors, specifically the refractive index, the UV-Vis photodiode array, the light scattering, and the viscometer detectors are housed in OMNISEC Reveal, the detector unit. The OMNISEC software allows us to measure the concentration, absolute molecular weight, intrinsic viscosity, hydrodynamic radius, and molecular structure of a sample from a single injection. Additionally, the OMNISEC software makes it easy to set up a sequence of samples and also calibrate quickly by taking into account the calibration factors, detector offsets, and all band broadening adjustments that are necessary. Another feature of the software is that it allows you to make side-by-side comparisons between samples or sample injections, whether specifically you're looking at numerical comparisons, which are demonstrated in the result statistics table, or visual comparisons, which can be seen in the various overlay plots and chromatograms available. So I hope you've gotten a sense today of what it's like to use the OMNISEC system. If you have any questions, please don't hesitate to get in touch with the Malvern representative. Thank you for your time and attention.
Thank you for listening. For more information, please visit www.malvern.com.